महेश एक ग्लास पानी आण हं? थोडा वेळाने आणलं तरी चालतं एक ग्लास पाणी आणून ठेवलं प्यायला ते प्यायला चांगलं वाटलं
Good morning, all the participants. I welcome you all to the SCTP program on advances in the field of civil engineering, day two. For session two, we have with us Mr. Suneel Voditel. Sir has more than 30 years of experience in structural design, and he has delivered more than 10 million square feet of structural design, delivered more than 10,000 metric ton of steel projects. Sir specializes in planning and design, industrial building design, RCC multi-story buildings, steel structures, and large span roofing, construction supervision and management, retrofitting and structural health monitoring. Sir have got many awards in Indian Concrete Institute Ultratech Award for Outstanding Concrete Structural of Vidarbha for design of Persistent System Limited IT Park commercial building, which was around 4 lakh square feet in 2012. ACC ACCE Annual Award of Excellence in Consultancy for design of industrial project of Suguna Poultry Farm Private Limited. It is a solvent extraction plant and power plant in 2010. Institute of Engineers India Best Paper Award in 1996. Institute of Engineers India Best Lecture Award in 1990. Sir's educations are like this. He has done his ME from Indian Institute of Technology, Roorkee. He has done his engineering from VNIT College, Nagpur, and Sir has done completed many projects like Integrated Industrial Township, Greater Noida, Aurangabad Industrial Township Limited, Lakshya International School, Bihar, IT Park Building, Nagpur, Rope Hotel, Dubai, Celio Industry, Gujarat, and the list go on. Uh, now I request Sunil sir to start with this session.
Yeah. So, good morning, everybody, for this wonderful program that has been organized by Anjuman College of Engineering and Technology in association with Indian Concrete Institute. At the outset, I would first like to thank the management of Anjuman College of Engineering and all the faculty members involved in this organizing this program for taking efforts and uh, giving us an opportunity to share our experiences and learnings in the field of civil engineering. I would also like to thank the chairman, Dr. Hitendra Chandawar, then all the office bearers of Indian Concrete Institute for taking this wonderful initiative in collaborating. And this is, in real sense, the industry institute interaction, and I'm sure that all the participants would be benefited by the galaxy of co-speakers. I mean, there are many more experienced people who would be delivering the talk during this program, and I'm sure everybody would be very much immensely benefited by this. So with that, I would want to start with my presentation. So, but before that, I will just like to say that purposefully I have taken and I have been doing sessions which are of practical interest. I don't intend delving into the theory part of any of the structural designs or the analysis, but the idea is to make it more interesting. The participant should be able to feel the structure in totality. It should be such that they should understand the basics. What happens is, in the engineering colleges, what we have, I have also been a student, I had also been a teacher. So what happens is, we are given information in bits and pieces, and for the student, it is very difficult to connect those dots. So what happens is that since he is unable to connect all the dots in the complete process of construction, be it starting from the planning, the design, the construction, till the end and the execution completion, whatever you call it. So what happens is that because he is unable to connect the dots, he will lose interest. At times, I've been observing that people tend to lose interest because of not being able to connect through the complete process. So, my idea or my concept is to make it a lively session, in the sense that whatever projects I have been doing all these years, I have taken 5 case studies. I have at least 40 to 50 case studies of this type. Maybe if I get an opportunity, I'll be very glad to share those also. But for today's session, I have chosen 5 of my case studies, and they are all unique in the sense that it does not only does it involve the analysis and the design, but there are certain very uh, very innovative intricacies, I would say, which are involved in the construction. So with that, I would take you to the case studies. This is a brief about me, which has already been, thanks to Mr. Azaz for having given my introduction. This is just a slide, a template as to how the structures are planned by the architects and the planners. So we'll quickly jump to case study one. This is a project which we have done in West Africa, and that is West African Soya Industries Limited at Nigeria in Africa. So the scope of this project was it was a solvent extraction plant, a plant where you extract oil out of the seeds. The seeds could be soybean, they could be rice bran, it could be sunflower, it could be groundnut. So basically, this is a plant, a complete plant where we were supposed to, our scope was to analyze and design the complete MS structure, and also do the foundation design. We were given the general arrangement drawings by the supplier, and the client connected us to the machine suppliers. We were given the load data, and for that we made extractable models. And I'll take you through the complete process where the shop drawings were generated. The best part is that we were able to execute this project sitting in India, Nagpur, and several thousand kilometers away. They followed our drawings in toto, and the plant was erected. The other building that we were assigned was a de-oiled cake building. It's a godown, it's a warehouse, and nothing big in this particular building, because we were supposed to do the foundation design. And also, the vendor was Kirby Systems. Kirby is an international giant in pre-engineered buildings. So we got the drawings, and we were assigned to check as a proof check their drawings for correctness. And mostly they are normally they have a very good team themselves. So there are very few errors, so to say. The other building was a cooling tower, which we will take through, and a hexane tank, underground tank, and some engineering stores, and some process trap, a small tank. So moving on to first, this is the image of the location of the plant in Nigeria. It's about 100 kilometers. It's about 40-45 kilometers from Lagos, which is the commercial capital, so to say, of Nigeria. So this is the Google's map. And this was the first input drawing we received from a company called Desmet. Now, Desmet is again a very, it's a very leading company in supply of edible oil plants, process plants. So what they do is they design the complete plant. They know how to put the vessels in at various levels, where to have the pumps, where there's an extraction unit. So all this is a general arrangement, and they give us the floor loads. The floor loads are given at different floors, and then we are supposed to choose the columns, the beams ourselves based on the load data, and then do the analysis, do the detailed engineering, and help the client get the structure fabricated. And parallelly, the civil foundations drawings are also required to be issued to the site So it happens in two phases. One is the civil foundation is executed on the site, and the structure is fabricated either in the workshop or in India at many locations. They do it themselves at the site itself. But there are certain challenges in getting it designed, getting it executed on the site, because there are issues of inconsistent current or power supply available at the site. Then there are some quality issues also. So generally, for such important plants, the plant should be got fabricated in a shop, a workshop, and then it is painted. There is a process called shot blasting and sand blasting. Then there's a process where they put the enamel paints, or either the epoxy paints are all the components are painted, and then they are so designed that they are just like Lego toys. Most of you are conversant with Lego toys. It's all plug and play. You should have everything nut bolted system, and then you send it, and they should be perfectly fitting each other, and that is how the erection process starts. So next is, this is another view. Here we have the sectional views of the plants given by the supplier. So this we call is the input drawing. So with this input drawing, the structural engineer is supposed to develop all the details. So the first step that we do is we prepare a STAD model. I'm sure most of the participants here are conversant with STAD. So this is the first step where we open the STAD model, we give the inputs and prepare based on, I'll just go back once again. So you get the coordinates of the plant from this drawing, that is the general arrangement drawing. You will also have some documents which will give the loads of the equipment at various floors. So also you will be specified, and at times if it's not specified, then you are supposed to consider the live load on different floors. Now live load means the load of the movement of personnel. Then there are some equipment which are to be moved, which are non fixed, so to say, which can be moved from one place to another for temporary, for the operational purpose, or whatever. So those equipment come under the category of live load. So we have to consider dead load, live load, the wind load, the earthquake load, and the snow load. This was a equatorial area, so no snow load. But there are cases where you have to consider all these loading and move ahead with the analysis. So the first step is to prepare a three-dimensional model. Here we had used the loading as per, we were asked to use the European code. So we had used the British standards BS 6399, then this, and the earthquake, they said, okay, you can follow the Indian standard. The grade of concrete that has been used is M30, and the grade of steel is FE 500. So these are other views of the STAD model, where you can see the braces and all the. This is also called a ball and stick model, or a skeletal model in structural parlance. Now this is the rendered view of STAD, in STAD of the complete plant. So here, this is the place where this model can be shared with the client. It can be shared with the supplier, who would also zoom in and see whether the beam framing suits him or not. There are a number of cutouts which are to be required for the process as per the drawing. So whether the input given by the supplier has been translated into your STAD model or not this is the place where the first cut you can check. There are some monorails to be attached. Here I can show, if you can see my cursor, there's a monorail for lifting equipment. So there's a path of the monorail which is given in the input drawing. So that also you have to model here. And the first iteration, let me tell you, is you have to guess some of the members, guess some of the column members and beam members, and then run the STAD and achieve a convergence. Now, any good structural engineer would want to optimize on the structural beams, but at the same time, you should remember that there should not be too many sections, because then fabrication becomes very difficult. If you get too many members, then the cutting length or the wastages are quite large, and that defeats the entire purpose of economy. So this is the analytical model where the properties have been assigned. Here you can see we have used the universal beams for the beams, and you see the universal columns uh, as per the we have used the universal beams and universal columns. So here the nodes have been highlighted as to what properties have been assigned. Similarly, you have the live load, the earthquake load, the dead load, all the loads and the load combinations, whatever is expected has been given here. All loads have to be considered. Now this is the place when once again you can interact with the client, or you can interact with the machine supplier and tell them that these are the loads that you have been considering, and if at all they find that some additional load is to be put on the structure, then this is the time where it can be done. Now once you have got a confirmation from the client and the machine supplier that yes, this model looks good, then you can do the this analysis. You can here you are getting the bending moment diagram and the shear force diagram, and one more is the deflection diagram. So deflections are the most governing, because if the see, first please remember that the deflections are the first to occur. If the deflections are under control, then the structure gets an opportunity to stress itself. If your deflections go out of control, then the stresses do not reach their peak values, in neither the bending nor the shear. And usually for steel structures, the structure will have a tendency to distort. See here, you can see some of the nodes flying off, they're going away. And but if this lateral deflection is within limit, then the structure is said to be a rigid, it is properly tied up. And from that point, then from that, you can get the bending moment and shear forces here. So now each and every member has to be checked for the maximum allowable bending stress and maximum allowable shear stress. And that is how a good structural engineer has to tabulate the sections that are required at different levels, assign them, reanalyze it, and this iterative process he has to do over and over again till he gets a good structure where the efficiency or the utilization ratio of the strength of the component is in the range of 80 to 90%. Let us not plan a structure where the efficiency is exploited more than 90%, because what happens is there are some imperfections during fabrication, and there may be some overloading of the structure, which at this stage we may not foresee. But so as a good engineering practice, as a good construction practice, we should have a designer should think and keep a margin of say 5 to 8% in his structure. That is always beneficial. So this is the deflection diagram, and this is the utilization ratio which I was mentioning. Here the allowable is 1, and you have reached 0.93, 99, 96, 98, and then subsequently these are for some members, but subsequently you are in the range of 0.877, 0.879, 0.8, 0.88, and so on. Now we come to the foundation design calculations. Here, once you have analyzed the structure, you will get the reactions at the various points, the foundation level. Now you have to club all the columns in one category, in different categories, and for a particular category you can choose the maximum axial force, the shear, the biaxial bending, and torsional moment also. There are 6 degrees of freedom in any rigid structure. I hope everybody knows that. You have 1 axial force, 2 shears, 2 bending moment, and 1 torsional. So in total, you have 6 degrees of freedom. So any rigidly connected structure, any frame structure will have 6 degrees of freedom. So you can expect 6 reactions. So using those 6 reactions, at times the torsional moment does not govern. So we tend to neglect that. And you can ignore that particular thing, and you can focus on the axial, which is the predominant force, and the biaxial moments. Shear is usually under control if axial force and bending moment is taken care of. So now with this, we have an Excel sheet where you put the grade of concrete, the grade of steel, the sizes of the columns, columns or the pedestals, and the height of the column, and then you put the data which is given in the yellow, highlighted in yellow, and then you get all the base pressures. What is the best? This I'll not elaborate much because this is a very simple tool. This is readily available on the net also, that how to calculate the foundation, the base pressure at the foundation. This pressure should be less than the bearing capacity of the soil. Then you have to also check for the one-way shear depending on the cantilever portion that is outstanding beyond the column face. So let me not spend much time on this. So next we come to the Tekla model. Now Tekla, what is Tekla? Tekla is a tool which will help a structural engineer model all the sections through software. It's a software where you can design all the connectors, the connections, and it will generate all the shop drawings. So Tekla is one company which is supplying the software for shop drawings. The other is Advanced Steel. Advanced Steel is owned by Autodesk. So either you use Tekla or you use Advanced Steel, and you can generate the model. So the beauty here is this model is directly input, is directly input from the STAD output. STAD output, the output of STAD comes directly into the Tekla. So these are some of the views of Tekla, where you can see that we have modeled the columns, the beams, the connections using Tekla. Now this is a closer view of the connectors. Now all these bolts, depending on the shear force in the beam, the shear has to be transferred to the column through the bolts. So you have 4 bolts on this side, 4 on the other. You have to calculate the thickness of the plate. You have to calculate the weld of the cleat to which it is transferred. So all these calculations are to be done by the structural engineer. There are some stiffeners to be provided so that the seat, this is called the seat should effectively be able to transfer the load from the beam to the column. The beam itself is designed. The section of the beam is for the bending moment in that beam and the shear force pertaining to the shear force coming in that member. And if you see the arrow here, this is for the one-way slab. Now the slab can be either a precast slab, it could be a metal deck sheet on which concrete is poured, it could be grating, steel grating, it could be checkered plates, and so on and so forth. Excuse me. So the connections here are for the bracing system. Here we can see here, and these are the foundation bolts that are being provided as designed. So based on the input, this is the first set of engineering drawing, which we called as general arrangement drawing of solvent plant, which is generated. And here we have to give the section list. Now this is very important because this is the first drawing issued by our office to the client to procure the steel. So what he does is he takes this drawing, he does his own study, and then he will transfer this drawing to the fabricator. The fabricator himself will study all the details, and then he will place the order for this, and that is the first step to start the fabrication. This is the second drawing where we again show these are the two-dimensional drawings, 2D drawings. One is we have shared the Tekla model, we have shared the these drawings, and the bill of quantities or bill of materials as it is called. So here these are the general arrangement where you show what all the braces and how they are there. Now these are some of the pictures of the site where you have you have issued the civil foundation drawings and the work has started parallelly. So these are the foundations. You have a miller here, and which is the foundation form work is ready for putting the concrete. Now these are the site photos. This is the model. This is the rendered. On the left is the rendered model which we had generated based through the software. That this is how it will look, and to the right is the actual erection. Now, this such type of technology is now available using building information modeling (BIM), as it is popularly called, where you first develop the model inside in your office, share with the client, and then also as the process goes on, as the process of erection goes on, then you can compare the model and see how it is complementing each other in terms of the planning and the practice. So these are some of the images of these are the equipment at different levels that they are placed. We were given the load data as about 30 metric ton, 50 metric ton to be kept here hanging from the floor. So 50 metric ton is a huge load. So we had to accordingly design the various fixing arrangements, how the load will be first transferred on the cleat, from the cleat onto the members, from the members to the secondary members to the primary members, and from the primary members to the column, and through the column to the foundation. So this is basically the chronology of the load transfer mechanism in any structure. So these are some of the views. The blue one which you see is the main heart of the plant, that is called the extractor. We were required to give all the detailing of the steps. Each step has to be accurately designed. It has to be actually detailed out in the Tekla model, and all the connections, because the plant is about 40 to 50 kilometers away from the workshop. So any change means it's a cost to the client. Suppose I miss out on one member here, or if the length is missed out, then it's a cost to the my client, and also a huge time delay, because if when the member is trying when the people at the site, when they try to assemble this member, and if they find it either too short or too long, then they will be the work will be held here for some time, and that member has to be the supplier has to be informed. Then he will manufacture that. Maybe he may have some other ongoing projects, so that he may ask for a 7 days time. Then that particular piece will arrive. It has to be painted, shot blasted first, and then painted, and then brought here. Then it has to be again measured and fitted. So the complete cycle is about 15 to 20 days. So you have to be very, very particular in this case. Any pre-engineered building for that matter. So these are some more views, and this is a closer view of the various equipment. These are actual pictures inside the plant. It's quite complex because the bracing systems are to be planned in such a way that you require the rigidity for the plant. At the same time, you don't obstruct the movement of the personnel, because if the process people who are going to operate the plant, if they find it difficult, then it becomes very difficult. So now I'll quickly run through some of the images, some internal views, and after about 7 to 8 months after delivering the project, at the last stage in November, I happened to visit the plant. They invited me, and it was a very hectic journey to Africa. But somehow, since it was the closure, and now only part of the sheeting was remaining, I was informed that now this is February, so the plant has already been commissioned and it's running well. Now this is the cooling tower. So this is the type of drawings that we have to issue from our office related to cooling tower. It's a tower where the water is cooled. So you can see this is the second drawing. We have to give there's a tray here, and on top you have the bolts, and then the cooling tower is which is made out of either wood, or it can be a fiber body. So that is mounted. So all the details are very important pertaining to levels, because we cannot communicate with the site because site is quite far away, and we have some timing issues also. They are lagging behind us by 4.5 hours. So, for example, now it is 10:30, quarter to 11, so it must be 6 o'clock there. So it becomes very difficult for them to catch up with our time, or for us also to catch up with their time. So this is the civil of the cooling tower. These are some tanks, underground tanks called the hexane tanks. So these are the details pertaining to hexane tanks. You have to design the wall here, the reinforcement. I'll not go into much of the details. These are the, you have to give the detailing of the bar, or bar A, bar B, and what all. Then if you want to have a haunch here for the better strength at the junction of the wall and the base raft, then that detail also is to be given. Then you have to give the details of the bolts. Then for a person to get down into the pit, you have to give some rungs like you have in the well, so that the person can, if you miss out this, then you have to resort to Hilti or some other company, which again adds to the cost. So this is the detail of the solvent water trap, where you have to make different compartments, all RCC, but everything has to be properly detailed. There's a hold fast here, how to connect one particular edge angle is to be given. Then all these details have to. So here for this, you either need the complete detailing from the supplier, or you have to raise questions. This comes with experience, of course, but you have to be very alert on this point, that you don't miss out anything and things are executed properly. So now this is the second general arrangement drawing that we have, civil drawing, which we have issued for the de-oiled cake go down. As I said, that Kirby was the supplier here. So Kirby has given us the reactions at different levels at the foundation top, and based on that we have generated the drawings. This is the related to the plinth. Now here two twin beams had to be given because there was excess fill. The flooring height was about 1.5 or even more, because the ground was low lying. So what we do is we give a first main beam, then put the masonry brickwork, and then again run a smaller beam so as to sustain the pressure. This is a cost saving measure. Otherwise, you can take a retaining wall from here, which becomes either expensive, not only expensive, but also it takes a little more time. So this is the another engineering store building that we had done. All the drawings we have generated ourselves. Then this drawing is to be sent to Kirby or other vendors for their quote. So we have to be very clear. This is based on the input we have received from the client, that we want the size of the building to be something like 20 by 30, and then it will be 2-storied or 3-storied, 3 levels. Then there will be a staircase on this end, and there will be an office on this floor, and things like that. So these are some of the images of the building. So with this, I come to the end of the first case study. Mr. Azaz, I think we should go ahead with the case studies and then come back to question answers. Is that okay? Hello? Hello? Am I audible? Yeah. Can I move to case study 2, Mr.
Yes,
Azaz?
yes, yes, sir, you can.
Yeah. Okay. So case study 2 is a project in Chandrapur. It's a it's a pharma-based project, multi-organics. This why I have chosen this, you'll come to know very quickly when you see the plant. This was the input that we got, that they wanted a warehouse of 60 meters by 60 meters, a column free space as much as possible, and this was the input drawing. They said that we want to have the various things planned. You have some raw material and some space for this and that. So this was the basic the input from the client. Then here you can see a sketch where they wanted some monorail on the cantilever portion overhanging, and whether they want to lift and place the some of the jumbo bags onto the trucks for loading, and so on and so forth. So this was their first input. So based on this, what first thing we did is we suggested that you go for the pre-engineered building, Kirby or Zamil Steel, or there are a number of vendors. But what was happening is that for this size of 60 by 60, the all the vendors, they were suggesting to have columns which were too many in number. There were about 15 or 16 columns which were coming inside the warehouse, which was not acceptable. And moreover, because for the stability of the structure, all the vendors, pre-engineered vendors, they were saying we'll need cross braces, which was not acceptable to the client. So I gave us a proposal that I'll make a pyramid out of your building. So I said we'll make it 60 meters by 60-meter pyramid. So he said, how many columns you will need? I said I'll go do with only 5 internal columns. So they were in the first meeting, they were surprised. They said, how is it possible? I said, let me work on it. Let me give you a proposal if acceptable. So, but then they said, if you give 5 columns, then maybe your structure will be heavy and it will be uneconomical. I said, no, I'll match the prices which you are getting from the pre-engineered guy, all the PEB guys. So with that, we started, and these are the first architectural drawings which we have generated, just to showcase that the system that we propose to give. And these are the views that we generated to show that this is what is in our mind. The hatch shows the brickwork. Above the brickwork, there will be sheeting, and then there will be a pyramid. And then we showed the foundation plan. We detailed out the foundation plan. We showed them that there will be only 5 columns. And then the proposal, they asked us for the estimate. Then we prepared the estimate and we gave them the costing. And then once they compared that with the similar quotes they had got from a pre-engineered building, and they were quite happy. They said, okay, it looks like, this was their statement, it looks like you will be able to match our expectations and our requirement, because there are only few columns. We said, yes, we'll definitely try to match your expectation. So these are the plain beam drawings parallelly we had to develop. And with that, parallelly we developed the plain drawings and all the related drawings and the roofing drawings, because the structural drawing also has to be developed so as to work out the costing. So here we had taken a box girder here to receive the trusses, because the spans were very large. So I'll tell you that the entire philosophy of this structure is open web structure. An open web structure is a structure where you throw the steel sections away from the center of gravity. You make it as a box. It's an open box where your moment of inertia increases, but the material requirement goes down. What happens in a pre-engineered building, which is the most popular these days, is they use plated sections because they have automated machines. Now, in a plated sections, they need a continuum. It's a continuity. You need the top flange, you need the bottom flange, and you need the web, which in our case, we can achieve a good saving by having an open sections where the shear requirement is very minimal. And that is the benefit of you going in for open web sections, open web structures. So this is our proposal. The purlins are very light purlins. For a 6-meter span purlin, you have 65/6 angle, a rod, and then you have some tie members here, and that's it. So what happens is the weight of this purlin is much lesser than the Z section that pre-engineered building people use. So here you have the turbo arrangement. Here we have, if on the right, if you see, you have a monorail which is running for, this is the cantilever portion, about 6 meters cantilever. 6 meters is not a less cantilever, it's about 20 feet. And where the truck can come and the jumbo back can be lifted up and it can be lowered down once the truck has moved away. So this is an enlarged detail. We have to see at the start itself, you have to give an arrangement of how the structure would be, so that the client is comfortable. Now, these are the pictures which we have generated. What I have proposed is, why we have adopted is 5 individual freestanding columns. They are at least 20 meters apart. If you see the general alignment, they are 20 to 24 meters apart. So you can have a box girder and you have a framing system here. Here, because the columns are slender, till such time that your structure is placed on top, there is a tendency of the columns to deflect at the top. But once tied up, it becomes a very rigid frame. So we have the columns 6 meters at in the periphery along the wall, which is acceptable to the client. But in between, you have only these 5 columns. So these are the very light trusses, but because of the pyramid, the advantage is that you have four direction slopes. There are little challenges, a few challenges in the cutting of the sheeting, because what happens is people have a tendency of cutting the sheets randomly, and then they say that okay, if you have a pyramid roofing, then there's a lot of sheet wastage. But let me tell you, and let me tell you confidently, that the sheet utilization can be minimized if you do a good planning, and the sheet which is cut from one part can be reused or used in the other part. So practically there is very little wastage, even if the roofing is of a pyramid type. So, but the beauty here is that you have to detail out such connections where at different levels you have to receive the trusses and achieve it. Now, I have one more case study of similar type where the shed is 80 meters by 80 meters. I think that is the third or fourth case study. So I will not spend much time on this. So this is the cantilever here, and this is after the post sheeting. I don't have the actual latest photo, but might would have been more clearer. But yeah, this is the yard where the fabrication was done. It's a simple. This is MIDC Chandrapur on Gugus Road. So, in case somebody is interested, we can just organize an event visit also with their permission. So, this is during the erection. This is during the fabrication. You have to check the weld length of this. Then this part has the red oxide, and the rest of it has been painted. And this is the special louvers that we got made to match or to make the shed look similar to pre-engineered building using plated sections. And these are some of the images where the erection has progressed even further. And now this is over a year and a half that the shed is completed, and they are very happy because they are only 5 columns. They can take the hydra and move other material from here and there, and there's no hindrance absolutely. So now coming to the third case study, and that is the clubhouse. This is a project which is too close to my heart, and it was a very challenging project, and I took it as a challenge. So this is the location. The location is Sadhu for Avinash Group. They are very big builders in Raipur, and they have a township called Capital Homes 1 and Capital Homes 2. So in between the two, this is Capital Homes 2, next to Capital Home, they had planned a clubhouse and a swimming pool. So this is the swimming pool, a clubhouse, and a badminton court. So this is a badminton court. Yeah. So the first image that was shared to us was something by the architects. I must congratulate the architects for a creative group from Delhi for planning this excellent structure. They won a number of architectural awards even prior to our starting the work because of the creativity. In some of the journals, they had got this printed and published, and then these are the views. These are the rendered by through Grasshopper, and maybe they started with SketchUp. Mostly architects love to work with SketchUp, and then they migrate to Grasshopper and Rhino and things like that. So the challenge was that this is the swimming pool, and this was, and to the right is the badminton hall. So these are the images, and then we were told that now you have to develop this structure. Now, friends, let me tell you that whatever we study, beam columns, is the basic of what you have to struggle, what you have to achieve in life as a practicing structural engineer. The fundamentals are the backbone on which you have to mount. So when I see people saying that, oh, we are doing only beam and columns, no. The beams and columns you have to do for a couple of years, and then you can migrate to structures which will have the same principles. What I'm doing is nothing different from the structural engineering that I have learned in college. It's only the application that I have been able to migrate to, or to graduate to, I should say, to achieve a structure of this type. So with this, these basic images, The challenge was thrown to us. So what did is, this is called the wireframe model of the same. So using the Rhino software, we asked them to generate us the skeletal model based on which they had done the planning. And then what I did is, we our team, what they did is that they sliced off the entire model, because here the first thing that was important was to capture the coordinates. See, unless you have the coordinates, you cannot put it on the two-dimensional drawing. And if you are not able to put the two-dimensional drawing, you are not able to communicate to the site. And if you're not able to communicate to the site won't be able to execute it. They will ask you, what is this point? With reference to some point on the ground, you have to give X, Y, and Z coordinates. So that is precisely what we did. We took out the coordinates using the Rhino software. We sliced off a number of sections. See, here you can see 1, 2, 3, and some 9 sections here, and a variety of sections here, X, Y, and Z. So when the images that show here is relate to that, here the frame is there and some hood is there, but other things are missing. Here the hood is in two parts. Here the hood is in two parts with a tail. Here there is no hood, only part of the body. So that is how we could understand the complete geometry, a three-dimensional geometry of the structure. And this is a rendered view of the clubhouse. This is generated by the architect. He shared this with us to show that this is what is expected. And the squash court, which is inside the clubhouse ground floor. And this was the image, the 2D plan which was shared to us. So with 2D plan and the rendered views, it was a kickstart for us. So here you had the staircase here. You can see here the spiral staircase. Once again, I'll repeat. This is the badminton hall, the swimming pool, the main clubhouse, which is ground plus 1 story. And on the ground floor, you have the squash court, and you have the other things here with some pool table or something. And here you have the toilet block and the entrance. Now, these are the drawings which we have generated to the RCC drawings, where they wanted the folded steps for the staircase. The entire staircase is cantilever. From the images you'll see, and this is the schedule and a few sections of the main beams, and this is once again the badminton hall. The badminton hall structure, the trusses and the purlins, the detailing, some brackets on the column which to receive the trusses of the badminton hall, and things like that. And these are the preliminary foundations, because this was again a guesswork, because the civil was going on. They asked us, okay, your columns, how are you going to generate the shapes? So we said that we will have the tubular structures, a three-dimensional lattice type of structure. So they said that from where it will start. So we said from the ground floor, because we need the support. So they said, okay, you give us the columns and sizes and the structure. And that is how we started. So these are some preliminary drawings which we generated. The RCC photos during completion. This is the truss of the badminton hall, the structure, RCC structure. The RCC structure. Now here, this height is 6 meters. For those who want to just understand the scaling effect, the height of the complete structure is about 12 meters. It is as tall as a 4-storied building. But here, this is 2-storied building, 3 plus 3, 6. And because the columns are getting terminated here, and they wanted the shell to rest here, we were asked to have the columns of this shape. This is the folded staircase, fully cantilevered from the shear wall. So you can see here. Here there is a beam. See, these steps are cantilevering out from the beam, and there is no wall here. And these are the completed pictures of steel structures of the badminton court. Now, this is the point where we started. They had displayed this image at the site. Then, just to in the township, they wanted to showcase every occupant in the or in the tenement in their township, they were curious to know. So what they did is, as we started the work, they displayed that as a big billboard on the site. And then people were just, we were more scared because the people knew what is to happen, and we were very, very ignorant of what we are going to achieve. And gradually we developed these sections of using three pipes and then doing some lattice. See, let me explain that had I used some heavier sections like I beams and etc., then the weight would have been very phenomenal, and the three-dimensional rigidity would not have been achieved for the least mass to weight, weight to this ratio, what you call weight to efficiency of the structure. So I wanted a lighter structure and tubular structures with thinner thicknesses, because not much of load is there. It's just the shape that has to be achieved. Working with angles would have been, although we have used angles for some columns, channels also we have used, but curving the angles and curving the channels becomes a bit challenging. So we have selectively used them as and when required. So these are the photographs with my team and the fabricator and the architectural architect here from Delhi, their representative. And this is what we did is we have applied the ferrocrete on top of it. We put the chicken mesh, weld mesh, first the weld mesh, chicken mesh over the steel skeleton, and then applied the concrete, micro concrete you can call, or ferrocrete as it is popularly known. So this is the typical section of this is about 65 NB section. The sample of the weld mesh and chicken mesh put on it, and this is the staircase. So these are the different pictures of during the construction. We had to make an arch here, so we made it again in three pipes. And this is how gradually it was started and it developed. And then this part you have put the ferrocrete, and you can see here the basic skeleton and the ferrocrete, and is ready to receive the ferrocrete. And this is the internal view on the first floor. The length is more than 55-60 meters. The height is 12 meters here. Here it is about 8 to 9 about 10 meters here, and 12 and a half meters here. Here it is less, 6 plus maybe 3 and a half. And this is how the scaffolding is there, and the project is almost complete now. These are pictures of, I think, November, but now they are ready for even this part, which they are almost completed. And this is the front faces. This is the perhaps the latest picture of maybe December, where now they have the here the glass here basically, and the detailing has already been done. The glass would be arriving and it will be fitted. So now we come to the case study number 4. I don't want to waste much time here. Now again, the project which we saw of Chandrapur. This is second project again in Chandrapur. In fact, this was done prior to the 60 meter by 60 meter. Here, this is the image Google map. He has beautifully put a swastika on. This is the road which goes to Mancherial. This site is very close to Mancherial in Telangana. It's bordering Maharashtra, and the client is into ginning. Procurement of cotton, processing of cotton, making bales out of it and supplying it to spinning mills. So that was his objective. Once again, he came to us with this basic plan. See, this is our site. So he suggested, asked us for the compound wall drawings. He asked us details of the roads, the weighbridge, then some underground tanks, then office block. So as consultants, they want to have a single window system. They will not go to the architect. They will come to the structural engineer, civil engineer, if he is competent enough to give them a solution. See, aesthetics is what the architects are very good at, because that is their core subject. But as civil engineers, we must know the basics of any project. And if we are able to deliver drawings, if you are able to satisfy the client to his requirement, then he will not want another entity, that is the architect, for this, because here looks do not matter. These are process related projects. So most of the all these years, maybe 37, 40 years that I've been in practice, I have been handling projects of this kind where I take all the decisions, and that gives you a sense of satisfaction also. That okay, yes, for admin building etc. We ask him, we request the owner, you take a good architect on the board, because we are not the people to do the architectural features, but rest of the things like including plumbing design. If you start delving into the depth of plumbing design, it's all simple. We know the hydraulics, we know water has to flow from this point to this point. Now you can use your ingenuity, you can do some maths, and then you can work out systems and then give a solution. So here again, the requirement was about 85 meter by 85 meter, or maybe 80 by 80, sorry, 80 by 80. So here also we said, okay, we'll give you only minimum number of columns, and that they are 9 numbers. The smaller columns are just wall supporting columns, because he wanted a partition walls. Let me tell you to the new of our participants, friends, that you should never have this being about 20-meter long. See, 20, 20, 20, 20. So 20 into 4, 80. Whereas the outer columns are at 10 meters grid. And because the wall is to be placed here, you require columns at 5 meters. Because otherwise, your wall becomes unsupported. The brick masonry becomes unsupported under lateral load, even the slightest load. It could be because of stacking of material, or it could be because of the wind pressure variance between the two parts of the shed, that the wall is likely to collapse. Or maybe in a seismic case like yesterday Turkey quake, if the wall does not have intermittent columns, a framework, then the wall is likely to collapse. So you have to be very careful. So these are some of the details of the foundation. Practically, with this is the practical sheet which we have issued, and the construction has been done. So nothing has been added or deleted out of it. These are the fine detailing which one has to take place. You will not get these details in any of the books, because you have to think yourself the various connections where the trusses are going to come and rest, and then you have to develop, satisfy yourself, and then release to the site. It's very, very important that you don't miss out anything, because working at that height of 12 meters, if you have missed out any bolts, or if there's a mismatch, is inviting lots and lots of trouble. The client will never pay your fees if you mess up with the structure. So this is the bottom line. So 80 by 80 we did with 9 columns only. The pre-engineered building vendors which were consulted, about 5 or 6 people were different vendors were consulted, including Kirby. They had suggested 22 columns. Because I'll tell you why 22. Because normally in a pre-engineered building, the columns are spaced at 7.75 to 8.25. That is their standard spacing. Pan India, pan globe. They have a purlin which is 200 mm depth, 1.75 to 2.25 or 2.5 if the loading is heavy as the thickness. So for that, they have optimized the purlins, the Z purlins. So with that spacing, and they have optimized the frames, the spacing. So their spacing is 7.75. So with 7.75, they will have columns inside at 7.75. Now, there is a concept called jack beam. So what they do is they avoid the internal alternate columns, and they put a jack beam on which they receive the main rafter. The rafter which starts at 7.75 here, they receive on a jack beam which spans 15 meters. But even with 15 meters, the column numbers were about 15 or so. And again, the cost was exorbitant for them. The moment you use jack beams, then their tonnage goes up for the pre-engineered by people, and they will automatically transfer it to the owner or the buyer. And that is where the catch is. So here we gave them an option, and we said that, okay, we will match, or even our cost will be lower than civil plus structural cost would be less than what the pre-engineered building supplier. At the same time, you will get a lot of freedom inside the warehouse. So these are the enlarged details of how the structure has been placed on top of the columns. These are the total global view. You can say that for the client, first the fabricator or the client has to understand what arrangement, structural arrangement. These are the knees for lateral stability, because these spans are very large. You need these ties or the knees. These are the purlins are triangular purlins in our case. Triangular purlins, if you visit any of the railway stations, the most optimum purlins are deployed by the railways, and that those two about 50 years back or 60 years back, because done by the Britishers, they have found that the open web sections are the most economical, and that is why you have hundreds and thousands of railway stations across India, but none of them have any other purlin type than the triangular purlins. So these are some of the further details. And this is the first picture. You can see the cotton being stacked here. The beauty here is that because you have very few columns, 9 columns, you can take the truck inside, do the unloading. During rains, you can do the loading. You can have the forklift moving back and forth, and this is the arrangement. But there are certain challenges here. See, this secondary truss has been received on the primary truss. There are a number of primary trusses reaching at the same point, so the detailing becomes very critical and has to be planned very meticulously. This is the night view during erection. One more advantage of having an open web structure where you have the triangular purlin and box type of wood trusses is you can avoid the bracings altogether. The structure does not require any bracings for lateral stability because you are tying up in a three-dimensional skeletal way. The complete trusses are tied up. You have the runners at the bottom, a few of them, and the purlins at every 1.5 meter centers. So it becomes a very rigid structure. You can have very large spans here. And these are some of the views, how the column, we have made a cap here because you have the lateral ties also to be received on the same cap as the main trusses. And these are the machines placed for the ginning, where you have the cotton coming, the raw cotton which is clean, then you have the cleaning process, and then they take it out, then they remove all the lints and etc. And then it is packed and then made into a bale and sent to the spinning mill. So this is the conveyor here on the left and different machinery in here. But you get very good headroom, and the columns, let me tell you, the columns do not have any plinth beam nor any tie beams. No RCC work except the columns. The columns have a good footing size, and there is no plinth beam because you cannot provide a plinth beam of 24 meters. If at all you want to provide a plinth beam of 24 meters, then you'll need some secondary beam secondary columns, a very small size, 4 feet by 4 feet, with a stub. We call it C0 columns at every 6 meters. But that again is time consuming and a cost ineffective method of designing a structure, because site is in too much of a hurry. Once they open up the site to start the work, they want to complete it as quickly as possible. So this is the swastika at the top, which is seen from the highway. This is going to Ramagundam, from Mancherial to Ramagundam highway. And this is the long shot. And these are some more views of the during erection and during completion. This is the fabrication going on. And yeah. And with this, I come to the last case study. I think we have about 15 minutes, and I can complete in 10 minutes, and we'll have 5 to 10 minutes of question answer session. This case number 5 study is a Mani Ratna celebrations. This is a hall in Amravati, about 150 kilometers. This is Nagpur Amravati road. You have a lot of new projects which have come up, City Land and Busy Land, those who are conversant with this part of Maharashtra, Vidarbha, is this is a fertilizer plant. Earlier it was a fertilizer plant. In fact, coincidentally, I had designed the roofing and the complete structure of this 1 lakh square feet about 22 years back. It was in 1999-2000 that I had designed the warehouse for fertilizer. They have a big fertilizer plant. Now they wanted to convert this into a celebration hall, because what happened is with passage of these 2 decades, the city limits got extended. So what was considered as an outskirts of Amravati came within the inland. It became a prime area which is surrounded by all the business community. There are a lot of retail and wholesale cloth market has come up here. So the people thought that, okay, as in any other city, why not have a celebration hall where we can have a hotel, and you can have marriage, number of marriages in the premises. They have a beautiful about 20 acres land here. So in that 20 acres land, they thought that why not have them. So it was the fertilizers earlier, 30 meters by 100 meters with a central row of columns for storing fertilizers. It was constructed about 21 years ago. And there are lean-to sheds, 15-meter each side, again designed by me then. And open footings, 7 feet level, because it's all black cotton soil. It's all black cotton soil. And the RCC columns, which were of 230 by 450, were only 6 meter high, because the span was only 15 meters. So these column sizes were 230 by 450, about 9 inch by 18 inches. And the trusses were in MS angles. Now, the city limits got extended. The client wanted to convert go down into celebration hall for large, for marriages and large gathering functions. So what struck him was he wanted to remove the central row of columns completely. This was the hurdle, that the go down of 30 by 100 had a central row of columns which had to be removed. So these are the columns, and this was this plan to have a banquet hall 1, which is bigger one, banquet hall 2, banquet hall 3, and then he had dining area planned here for 1, 2, 3, and a kitchen. So kitchen to serve all the 3 dining halls and the banquet halls here, and this is called the pre-function area. When you go to any function, you have an area where you have a meeting place initially. That is called a pre-function. Before you enter the main function, you have a lounge sort of an area which is a pre-function. So this was their planning, to have 3 different marriages going on simultaneously. You have 3 different dining areas and a single kitchen to cater to all the dining areas. In case they don't get booking for these 2, they might as well have only 1 to be rented out. It could be 2 at a time. It could be 3 at a time. So that was their thought process. But the biggest hurdle was the columns to be got removed, because without the column free area, this would have been a failure. So they, since I had designed it, they approached me, but they approached me the last. Very interestingly, they approached all the structural people outside Nagpur. They told me themselves, the owners, that we went to Delhi, we went to Chandigarh, we went to Pune, and we consulted number of structural engineers. Everybody refused, saying that this is not possible because it's very difficult. Your footings are very less. Your footings are very small, and it's not possible to strengthen the foundations. So they came to me and offered me that, sir, if you could do it. I said, yes, we can do it. They said, what will be the timelines and what will be the modus operandi of achieving this? So I said, okay, our footings are small. I agree, because that's a compliment for me, because I had designed this very economically 21 years back, but now I can strengthen it. So how we would strengthen it? I said, we can put some 2 piles, jacket the columns, put a cap, and achieve it. So, and he said, what about the truss? I said, the top 2 members which you see here are the trusses which were initial, and you had the column. I said, we will put some additional members and strengthen the truss to span 30 meters. A truss which was spanning 15 meters can be very easily converted to span 30 meters by strengthening. So for this, we did a STAT analysis of this, a 2-dimensional only. Ideally, one should do a 3-dimensional, because these are all planar structures. You can, if you are good at understanding the behavior of a structure, you can as well do a 2-dimensional analysis and strengthen the structure. So that is precisely what we did, and I'll just play the video. The columns were removed. I hope you are able to see the video also. The central row of columns, they were cut by supporting it. One more time. And this is the detail of the strengthening. That what we did is, this was the existing footing and column. We cut the part of the footing here, and then we engaged a piling contractor, got the piles done, about 375 dia, 2 number piles. We put a cap here at top. The cap was very well connected, and the column size also was increased by jacketing, by rebarring and converting into the other details. And over and above, we put some angles here and increased the size and filled up micro concrete here in between to achieve a massive size. The size was not that important, but we wanted to be very sure. And some here, bolting was done here using sleeve and all those things. This is a very standard detail, and maybe some people are doing it this better than me. Uh, and this is how the top one is the existing structure, and the lower members, these are the strengthened ones. We strengthened this, and we had used some connector flats, and then there were intermittent flats also which were done, and then existing column to be demolished. So this is how the strengthening was done. Some more details, some enlarged details. We had to use some gusset plates here because to get the adequate weld length, it is very important that you have the connector plates here called the gusset plates, and some connector flats, etc. And these are the standard drawings which we issued. And you can see that as a challenge, I told them that whatever is the span, I will make you stand on top along with loading 2.5 times the loading that is anticipated. So he said, "You suggest me a scheme." I said, "You can take slings, ropes, and then you can put at regular intervals on the from the truss and load it, and we'll stand together on this and prove that the structure can take 2.5 times the load." And that is precisely what we did. This is the image of the structure. Here the columns have been cut and the structure has been strengthened. And he's the owner and his son with me and my colleague, and we are demonstrating that yes, when you have a factor of safety of 2.5, now what are the weights that are going to come, that we had asked them. Now what are the weights? He said mostly plaster of Paris, POP ceiling, the false ceiling, some ducting. So those weights he gave us. We applied a factor of safety, and then accordingly he had some fertilizer bags lying in his warehouse. So we said, why not you put them, why not weigh a couple of bags and then stack them together. And these are the detailing. This plate is very important because that is the place where the deformation is likely to happen. And purlin, even the purlin, we strengthened it and made 5 people stand on top to just to demonstrate that it is a very strong structure. And the column has been jacketed with angles, and we had filled up concrete up to this level. And this is a video where you can see here a very small clip. There's nothing here. This is 30-meter span.
और वो उधर ज्यादा हो गया, ज्यादा नहीं उधर हो गया ना, बहुत ज्यादा तो बोरा डालना नहीं नहीं उधर 6 बोरी है और यहाँ देखिए यहाँ 5 है, सब जगह 5 ही अभी डाला है। आज जो 6 डाला है टोटल 5 है, आज कहीं पे भी 6 नहीं है, पर ये आने वाला है अभी आने वाला है। अरे वो डालते हैं कैसे डालना है आपने, वो उधर ही डाला ना, इधर ही ऐसा ना पड़ेगा, सिंगल डालते हुए नहीं उधर है अब क्रिटिकल।
We were more worried about the asymmetric loading, so I'll just play this one more time.
मत डालो ना, आता टाकू लगा त्याच्यात आणि एक तर और वो उधर ज्यादा हो गया, ज्यादा नहीं ज्यादा नहीं उधर हो गया ना, बहुत ज्यादा तो बोरा डाला नहीं नहीं उधर 6 बोरी है और यहाँ देखिए यहाँ 5 है, सब जगह 5 ही अभी डाला है। आज जो 6 डाला है टोटल 5 है, आज कहीं पे भी 6 नहीं, पर ये आने वाला है अभी आने वाला। अरे वो डालते हैं कैसे डालना है आपने, वो उधर ही डाला ना, इधर ही ऐसा ना पड़ेगा, सिंगल डालते हुए नहीं उधर है अब क्रिटिकल।
And these are the finished pictures of what we have achieved post strengthening. They have done all the POP, and this is the column free warehouse. And this is again some during the interiors. The final one is still better, much better, and yeah. So we could achieve this 30-meter span, and these are the plaster of Paris, the loading that was there, and this is the pre-function area, and this is the finished 30 meters by the first part is 60 meters or so, 30 by 60, then you have 30 by 20 and 30 by 20, something like that. So with this we come to the end, and I thank everybody for giving a patient hearing to my experiences and a few case studies which I have presented today. Mr. Azaz, I am open for questions.
Participants are requested to post the question in the comment box. I request all the participants, if they have any questions, they can post in the comment box.
Yeah, if you have till such time that you get the questions from the comment box, if you have any anybody who's asking ready to ask questions, I'll be more than glad to answer. Yeah, there's no requirement of expansion joint in a steel structure. Mr. Vinayak Vaidya, yeah, the code does not require for 180 meters. You don't need any for any expansion joint for a steel structure. And for the columns, even we had taken care of that in the analysis itself, because the thermal expansion, it's a linear wall, so it does not matter. We had avoided that. It's a good question. Yeah, only one question. Any more questions, please?
Okay, participant, I will share the feedback link in the chat box. And if you have any question related to Sunil sir's topic, you can ask in the feedback. Then we'll mail that feedback to Sunil sir, and if he is free, then he will revert you back on that. Is it okay for you, sir?
Yeah, perfectly fine.
Okay, then we will conclude the session. Thank you, sir, for this informative session and giving your valuable time to us. Thank you so much, sir.
So thank you everybody once again. Thank you ICI. Thank you Anjuman Engineering, all the staff and the administrative people around. Yeah, thank you very much. So can we
Okay, thank you,
conclude
sir.
now? Can we
Yes,
show?
yes, sir.
Stop?
Yes, sir.
Yes.
Okay, sir.
Okay. Thank you very much.
Thank you so much, sir.
Okay.